Okay, fine. In the previous class, we have discussed about the mean flow stress, and I also told you that please do refer the theory of failures. I mean the two theory of failures that are those are Rankine's, oh no, Tresca's theory and the von Mises theory. So have you done that? Any one of you? Any one of you have gone through the basics of Tresca's theory and the von Mises theory? Okay, good, very good. And also in the previous class, when I asked you about true stress and engineering stress, and also true strain versus engineering strain, nobody was answering the question. So I have put the derivation also here. So I have already clearly mentioned that the engineering stress is this, that is sigma is equal to P by A naught, isn't it? And that is A naught is the original cross-sectional area. And I told you already, true stress is nothing but P by A, where A is the instantaneous area. And also I told you that sigma T is equal to engineering stress into engineering strain plus 1. But I didn't show the derivation. So this is how the derivation goes. This is P by A, right? So this is P by A. Okay, let me take this. So this is P by A, and you can just multiply and divide by A naught, A naught. It doesn't matter, right? So it's a simple manipulation that we are trying to do here. And P by A naught is engineering stress. So this P by A naught is engineering stress, and A by A naught is left. And there is this thing called volume consistency. Obviously, if you are trying to apply some load onto your member, it doesn't change its volume because you're not removing it or you're not adding it. So it has to maintain the volume consistency. So initial volume will be equal to final volume. We know that. Or initial volume will be equal to any volume at any instant, right? So that's the reason why we are writing this A naught L naught, that is initial volume, is equal to instantaneous volume, A into L. Then A naught by A is L by L naught. Hence we can substitute that A naught by A by L by L naught here. And here again, I'm doing some kind of a trick. And that trick is L by L naught minus 1 plus 1, right? So minus 1 plus 1, I'm just adding and subtracting, right? So this is L minus L naught by L naught plus 1. So L minus L naught is delta L by L naught. Delta L by L naught is your engineering strain. So that is why we are writing as sigma into epsilon plus 1. Yes, good. Now let's proceed. So the next is true strain. And here also I've said it is dl by L, integration of dl by L, right? And we are integrating this thing with us from L naught to instantaneous length L. And that is ln of instantaneous L by L naught. And again, I'll add and minus 1 plus 1. I'll do the manipulation that I've done in the previous one here, right? This manipulation, I'll be doing the same thing here. So as we have got L minus L naught by L naught plus 1, and all these things we got as epsilon plus 1, right? The same thing we'll be getting here as ln of epsilon plus 1. So this is the formula I've told you, that is engineering strain, true strain is equal to ln of, so the bracket should be here. The bracket should be here like this. Okay, fine. So that is how, that is where we have stopped in the previous class. So let's proceed. So this and all is the flow stress curve. It's not very, the full derivation that I've done, but I'll tell you the important points. Okay. So you know that this is your stress strain curve, and this is where the ultimate tensile stress. So if you are doing your strength of material subject, I think it is going on, I guess. So if you're doing that, if you might have seen, you might have observed that this is your origin, and what is this? There are some points that you might have noted, right? So this is your this thing, and this is this thing, this is this thing, this is this thing. There are some points denoted. Let's say this is 1, 2, 3, 4, 5, 6, 7. So what is 2? 2 is, what is the 2? 2 point, anyone? The 2 point is denoted by what is the point? What is that name of that point? Anyone? 2 corresponds to what? 3 corresponds to what? 4 corresponds to what? 5 corresponds to what? Anyone? Tell me 2. What is that? Yes, this is proportional limit. 3 is elastic limit, upper yield point, lower yield point, ultimate tensile stress, and then he has the fracture, right? So the important point that we have to carry on, forget about all these things, that is at UTS, at ultimate tensile strength for mean flow stress. Man, this is your simple stress and strain curve, right? At ultimate tensile stress, okay, at this point your n will be equal to epsilon is true strain, okay, epsilon is true strain. And please remember, this is true stress was true strain graph, not the engineering stress was engineering strain graph. Please do understand that. And at ultimate tensile point, this is equal to this. So this kind of a question can be asked in the examination, and the derivation goes like this. And it's not good that we go and do details of this, because it's going to take longer time for us to understand what is happening here. So don't worry about it. For the sake of examination, please try to remember this or memorize this, that for the engineering for the true strain stress curve, the at the ultimate point, your strain hardening coefficient, this was the equation, isn't it? Sigma naught is equal to k epsilon to the power of n by n plus 1, isn't it? This was the equation, right? So at ultimate tensile stress or ultimate point, your strain hardening coefficient, this is what strain hardening exponent, this is strain hardening exponent, this is strain hardening exponent, right? So the strain hardening exponent is equal to epsilon t, that is true strain. So very important point that you have to note down. Okay, fine. Next. So that is what is very important. You have to note that. Next. So I told you that please do refer or please do the revise the Tresca's maximum shear stress criteria. So here we are going to, what we are going to do is that, let us assume that what is okay, fine. When we are doing like this, we are having something like this, and we are doing a test. Let's say if we are doing a test, then what happens? If you're doing a test, what happens? This is a tensile stress. So it's going to yield at some point. That is what you have seen, right? It's going to yield at some point. This is where the yielding is happening. After this is plastic zone. So this is tensile, right? So in shear in the sense, like you have some kind of a block like this, and it is attached to the ground. So this is attached to the ground, and you're trying to apply this force like this, and this is what? This is a shear force that you're applying. In shear also, obviously, it will yield. It yield in the sense like it will go to some position and it won't come back, right? And that yield, that limiting value of yield stress, let us assume that it is K. Okay. Please remember, we are doing this for shear force. Okay. And then for any loading, you have three principal stresses, right? In three mutually perpendicular axes, we have three principal stresses, right? That is sigma 1, sigma 2, sigma 3. Obviously, we are arranging all sigma 1, sigma 2, sigma 3 in the descending order, right? Fine. Now, please assume that the tau max is maximum shear stress. So if you are drawing more circle, if you are drawing a more circle like this, you're drawing a more circle. So what is this? This is your tau axis, and this is your sigma axis, isn't it? This is your tensile, this is your shear. So if you're drawing a more circle, this is what is tau max, right? This is what is your tau max, and that is what is your radius of your more circle. If you have already done all these things, it will be very easy for you to understand. Have you done these things in strength of materials? Yes or no? Have you done these things in strength of materials, guys? Hello, guys. Am I audible? So yeah. So these things, R is equal to tau max. You might have done these things, right? This is radius of Mohr circle, and this is your yes. Very good, very good, very good. And you might have also done this thing. What the tau max. So okay, fine. So according to Tresca's criteria, if you have revised this, you might have seen that the tau max is nothing but maximum stress minus minimum stress. This thing actually, it's nothing but sigma 1 minus sigma 2 by 2 comma max of, it should be like this. Actually, if you are trying to do it, it should be like this: sigma 2 minus sigma 3 by 2
comma sigma 3 minus sigma 1 by 2, something like that. Max of all the absolute values will take. But here in this case, what you're assuming is that, and this is what is the maximum value here. And now what we are trying to do, let's assume that this tau max, whatever the stress that we are trying to apply, should cross this K, right, for plastic deformation, because this is what is the yielding point. Obviously, this tau max should be more than this K, then only more than or equal to K, then only plastic deformation occurs. Then only plastic deformation occurs. But the limiting value is equal to, right? That limiting value is equal to. Okay, I didn't get Thakar. What is this? Yes, before class. What is this? Okay, you in strength of materials, you have seen this in before class, isn't it? That is what you're saying. Very good, very good. It's good then. It's very good then. Then I can go a little faster then. Fine. So this is what is this? Obviously, tau max is equal to K. So obviously sigma 1 minus sigma 3 by 2 is equal to K. Good, very good. And in von Mises distortion criteria also, what you're trying to do, this is what the equation is for the von Mises distortion equation. And we are assuming that the critical value here, we are observing that K is the critical value of shear point, and we are saying that A is the critical value of shear strain energy that reaches so that the plastic flow will happen. A is critical shear strain energy. Okay, so then we are equating this full equation to A, right? And then we got this equation. We got this equation, and we are assuming this to be a constant C. Okay, then now what we are trying to do is we are trying to do some tensile test. We are doing some tensile test. Okay, and in tensile test, obviously, if you know the other two directions, if you're having three directions like this, X, Y, and Z, if you're having three directions, if you're doing a tension test, you'll concentrate only on one axis. Other two axes don't have any stresses. That is what if you have already done, you know this thing. Now what I'm doing this, these are the conditions, right? These are the principal stresses. These are the principal stresses. Sigma 1 is equal to sigma y, yielding, right? And sigma 2 is equal to 0, sigma 3 is equal to 0. So substitute this in von Mises criteria here. Substitute this in von Mises criteria. If you're substituting, that is sigma y, sigma 1 is sigma minus sigma 1 minus sigma 2, right? Sigma 2 minus sigma 3, sigma 3 minus sigma 2, sigma 1, sorry. So this is 0, 0, 0, 0, 0. This is sigma y minus 0. So that is what I have substituted. Then this will become what? Sorry, there is some more. Yeah, this is sigma y here, sigma y. So this is 0. So here we have sigma y square. Here we have sigma y square. So hence we got 2 sigma y square is equal to C. Let this be equation like that. Let the equation be some 1 here, let's say. And the same conditions, same things we are trying. This is what tension. This is tension. And we are doing some shear now. We are doing it shear. We are doing shear. The same thing you substitute if you're doing a shear, pure shear. This is pure shear. This is pure shear. This is pure tension. This is pure tension. Okay. Now what you do, if you're having the shear, you might have seen the Mohr circle looks like this, right? This is your origin, and this is sigma 1, sigma 2, and this is the thing. So you might have seen already that the tau max is K, obviously, and sigma 1 is K. This is sigma 1, that is K. This is sigma 3 minus K. And sigma 2 is 0 because that we are doing it in 2 dimensions. We are not doing it in 3 dimensions, right? So substitute equation 2. What is equation 2? This one, this one Mises itself. If you substitute these conditions, these three conditions in this equation. So initially we substituted sigma 1 is equal to sigma y, sigma 2 is equal to 0, sigma 3 is equal to 0. This is pure tension. Now we are substituting sigma 1 is equal to K, sigma 2 is equal to, sorry, sigma 2 is equal to 0, sigma 3 is equal to minus K. This is pure shear. So this is tension, this is shear. We are substituting. So when we are substituted this thing, we got 2 sigma y square is equal to C. Now we are substituting this. After substituting this, what will you get? You'll get this. C is equal to sigma 6 K square. And here we got 2 sigma y square is equal to C. So C here, both C's are same. So hence we are writing 2 sigma y square is equal to C is equal to 6k square, and then we got to this equation, and hence k is equal to sigma y by root 3. K is equal to sigma y by root 3. Very important. So according to von Mises, your shear yield stress is equal to yield in tension, that is uniaxial loading only. Uniaxial loading only. Okay, you're not applying any other loading. Uniaxial, single inaxial. This is also pure shear. This is pure shear. Fine. So this is the important point you have to remember. This is what you have to remember. Shear in yield stress. Yield stress in shear. Yield stress in shear is equal to yield stress in tension divided by root 3. Very important formula, and that is according to which criteria? Von Mises criteria. That is according to von Mises criteria. And again, if you do the same thing, if you are doing what same thing, sir? If you're substituting this and this two, let's say this is 1 and 2. If you're substituting these two, 1 and 2, in Tresca's criteria, what was Tresca's criteria? Tresca's criteria was this, right? Tresca's criteria was this. Sorry, this was the Tresca criteria. So how can you substitute? So this is sigma 1 is y minus 0 by 2 is equal to k. So k is equal to sigma y by 2, right? So if you are substituting everything in Tresca's criteria, you will get k is equal to sigma y by 2. In the sense, yield stress in shear is equal to yield stress in tension divided by 2. Very important formula, I'm telling you again and again. This we are going to use again and again. People will not establish this thing, and they are going to apply sigma y by root 3 somewhere, sigma y by 2 somewhere. You don't know why you're applying, why we are doing all these things. We don't know. So many of you don't know. So many of us don't know that. That is the reason why I told you to revise this theory of failures and come back, and then we will try to analyze these things so that we have to know what is the relationship between yield strength in yield stress in shear. That is also yield. I'm telling yield, like yield is a very important point. Yield stress in shear is equal to yield stress in tension divided by root 3. Okay, that is for von Mises criteria. And for shear, what do you say? For Tresca's criteria, it is sigma y by 2. And if you have already done this in the previous class, who is more conservative? Is von Mises more conservative or Tresca is more conservative? Are you getting my point? What do you mean by conservative? If you have done this in previous class, you should answer me this thing. Von Mises is conservative or Tresca criteria is conservative? Who can say this? Anyone? Conservative in the sense, more realistic. Which criteria you want to use for your analysis? Do you want to use Tresca or do you want to use von Mises? In the sense, conservative in the sense, if more safe, who is more safe? Who is having more safety in these two criteria? If you're using Tresca, you're having more safety, or if you're using von Mises, you have more safety. What do you say, guys? Anyone can answer this if you know. It's not like that. So if we might have seen this, right? Like yes or no. I mean, I don't know. Like if they might have. I mean, in further classes you might know these things. So for Tresca's criteria, it is like this. You might have seen this thing, isn't it? Isn't it? Yes or no? You might have seen this kind of diagram for Tresca's criteria. And for von Mises, you might have seen it, that is the ellipse. It's kind of an ellipse which is inside this thing. This is for von Mises. So if the zone inside this is safe and that zone outside is not safe for von Mises, and the zone inside full, this kind of a hexagon or whatever it is inside that safe, and outside that is not safe for Tresca. If you might have seen that, did you see this? Yes or no? So again I draw the diagram. This is for Tresca, and for von Mises it is like this. Okay. Okay. So actually Tresca is having more factor of safety. Why? Because if you're drawing like this, if you're taking some point here, according to Tresca, it is safe. Sorry, I think it is inscribe or circumscribe. I don't remember actually. I should also see that. I think it is circumscribe. Yes, I guess. Yes, it is circumscribe. Okay. So according to Tresca, if you're taking this point, according to Tresca, it will fail. But according to von Mises, it won't fail. So generally, in reality, people tend to use von Mises than Tresca. Okay, because it is more realistic to the real. I mean, what you say, it is more realistic. It's like it's not ideal. Okay, so people tend to use von Mises for the conservativeness. Okay, so von Mises is the answer. Okay, fine. So generally we use this for more conservation. Fine, good. So try to note down these points. K is equal to sigma y by root 3. K is equal to sigma y by 2. Sigma y by root 3 for von Mises. Sigma y by 2 is for this thing. Fine. And before proceeding to rolling, I want to ask you the difference between plane stress and plane strain. Anyone who can answer these questions? Plane stress and plane strain. If you have done this, yes or no? Because this is also very important, because in examinations he'll ask rolling is plane stress or lowering is plane strain or rolling is both plane stress and plane strain problem. None of the above. What do you say? Which one will you select? First you have to know what is plane stress, right? So can you explain what is plane stress and plane strain? Anyone who can just say in one sentences. Plane stress is what? Or plane strain is what is plane strain? Okay, let's discuss first plane stress. Anyone who can answer this question? What is plane stress in a single line? Guys, hello. For maximum stress in a body, no. Okay, so I'll tell you. Plane stress. I'll write conditions. Okay, I don't want to draw diagrams and I'll take a long time. In plane stress, sigma x is not equal to 0, sigma y is not equal to 0, and sigma z equal to 0. In the sense, you're applying your stresses in 2D plane. In a plane, you're applying sigma y is there, but in sigma z direction, you're not applying any stresses. That is what is plane stress. Okay. So as sigma x is equal to sigma y is equal to 0, so you can say that epsilon x is not equal to 0, epsilon y is not equal to 0, epsilon z also is not equal to 0, because as you're trying to apply, we don't know. Your strain can occur in any directions. We are not sure about it because of these things, right? In plane strain, epsilon x is not equal to 0, epsilon y is not equal to 0, epsilon z equal to 0. In the sense, you are not allowing strain in z direction. So the strain in z direction is not allowed. Sir, how, sir, why, sir? We'll discuss that. First, we'll discuss what is this conditions. Then we'll come back and we'll discuss what is plane stress, or why rolling is plane stress, or why rolling is plane strain. Is it plane stress or is it plane strain? We'll discuss that. But we have to understand that in z direction, you don't have any strain. In the sense, you don't have any deformation in z direction. That is what you have to understand. What is epsilon z? Epsilon z is nothing but, if epsilon z is equal to 0, it means that no deformation or no expansion or no compression in z direction. That you have to understand. Very important. Okay, so now if and these three, obviously if you come to stress, these three all will not be equal to 0. Sigma y not equal to 0, sigma z also is not equal to 0. Okay, so fine, so let's not go into deeper. Try to understand that plane stress is nothing but sigma x, sigma y are there, sigma z is 0. plane strain is nothing but epsilon x and epsilon y are there. Epsilon z is 0. That is what you have to understand. Okay, in 2-dimensional you have to take. And if epsilon z, what does it epsilon z mean 0? I told you already that there is no deformation in the z axis, or there is no deformation in the other this thing. Okay, please try to understand that. Okay, now let's enter having all this basic set, let's go and discuss something on rolling. Okay, so if you see here, the diagram, it's a very beautiful diagram. I got it from somewhere. So this I mean, anyways, I couldn't get the reference here, but anyways, if in future if I have something, I'll just reference it. I got it from somewhere from the online. Okay, so if you see rolling, it's nothing but you have two rollers, roller 1 here, roller 2 here, and the roller 1 is roller 2 are maintained apart with some distance here. This is your roll separating distance. This is your roll separating distance. Roll are separated by this kind of a distance, and you have some slab, and that slab is trying to enter into the two rolls. In between two rolls, obviously this is some thickness T1, and this is some thickness, this is some roll separating distance, or maybe the distance between two rolls. And then obviously if you are trying to allow this thing in between, then the thickness will be reduced, right? The thickness of the slab will be reduced, and of course, as I mentioned here, T2 will be less than T1. That is what you want to get it, right? So, and so you can assume this is kind of an example. I'll give you some analogy for this, like the sugar cane, right? But I've seen that sugar cane juice. The guy is having some kind of two rolls, right? Two rolls are there like this, and then that fellow will put sugar cane in between. Did you see that? Yes or no, guys? Yes. So that is what. That is what. So if you're trying to apply some kind of this load onto the sugar cane, then only it will get squeezed, and then the juice will come out. Here, what happens? The dimensions are changing. Thickness is being reduced, and please remember here. Initially, the slab will be like this, having some length L and thickness T. Let's say T1, L1, and finally it will become a larger length L2 and smaller thickness T2. Obviously, T1 will be greater than T2 and L1 will be less than L2. But according to this thing, let's assume that this is width B1, right? And B1 is equal to B2. We are assuming that this is an assumption. B1 is equal to B2 in the sense, in the width direction, there is no change in dimension. In the width direction, there is no change in direction. So let us assume that this direction is X, this direction is Y, and this direction is Z. So X direction corresponds to length, Y direction corresponds to thickness, Z direction corresponds to width. If there is no change in length and width, it means that there is no deformation in Z direction. So is it a plane stress or plane strain? Plane stress or plane strain? What do you say? Is it a plane stress problem or a plane strain problem? Obviously it is a plane strain. That's it. That's it. You can easily go and say, you can easily suggest. And please remember, we are assuming that this is assumption only. Why we are assuming? Because for easiness our calculation. As we are assuming that, we can consider this problem as a plane strain problem. So please remember, if width is constant in rolling, obviously generally whatever we do, we assume that width is constant in rolling, and then we say that it is plane strain problem. Okay, so rolling is a plane strain problem. That is what you have to understand here. Good, fine. Now let's proceed. So this is a very fully written, filled with some these things, but anyways I'll break it down for you. So the top one is one roller 1, bottom is roller 2. and I'm going to 2D now because I assume that there is no deformation in 3D. So hence I'm taking a 2D diagram here. Okay. So now what we'll do is that we will enter this thing into this thing. So this H1 I'm writing as entry thickness. Instead of T1 and T2, I'm writing H1. H1 is the thickness of workpiece that is entering, and H2 is the thickness of workpiece that is leaving outside. So obviously you have to understand that H1 and H2. Who is bigger? H1 is bigger, obviously. H2 is lesser. And then the workpiece is entering into the working zone with velocity v1, and it is coming out with velocity v2. Okay, and this is the place. Okay, let me take this highlighter. So this is the place. This is the place where the deformation exactly is happening. So this is the place. The shaded one is the place where the deformation is happening. Okay, so if you see the entry is happening at this point, the entry is happening at this point, at this exactly this location, and exit happening at this exactly this location, but everything in between the deformation is happening. Okay, so in that, this is the point. So let me take either top and bottom. You can take any roller, but I'm taking a top roller. At this point, the point is which the incoming workpiece is starting or touching the roller. That is where the deformation is starting, and deformation, and this is the point where the deformation is ending, and the contact between workpiece and the roller also is ending here at point 3. So 1 2 3, 1 and 3 are the starting and ending points of the deformation, and there is another point 2. I'll tell you what is the 2. Okay, so if you see that this roller is rotating, like this. Roller is rotating with omega. If you see, this is omega. The roller is rotating with omega, right? And down one is rotating in clockwise, up one is rotating in anti-clockwise. That is the reason why the workpiece is moving from left side to right side. Okay. If you're trying to see, if you're trying to rotate like this, the friction between workpiece and roller will be in this direction, right? Sir, how, why, sir, the friction is in forward direction? Can anyone explain this? This is a very nice point, actually. So if you're having this thing, and this is a block, it is moving in right side with some force F. Friction will be in which direction, sir? Friction will be in which direction? Anyone? Obviously opposite to F. Obviously opposite to F. But here, and the friction F, this friction F is on which one? Is it on the mass block, or is it on the ground? This friction F, which is opposite to F, this friction small f, which is opposite to this capital F, is on a block or the ground. What do you say? If I take free body diagram, if I'm separating ground also, obviously it is on block. Yes, it is on block. Who is offering this? Who is offering this? This ground is offering. So hence, on block the friction will be on backside direction. Here we are balancing on block. But on ground, if you're considering that block is fixed and ground is moving on left hand side direction, because obviously that is what is happening. If you're sitting on block, then ground is moving backside, right? As you're sitting on ground and you're seeing the block, that is the reason why block is moving on right side and the friction is backside. If you're sitting on the ground, if you're sitting on the block, it means that ground is going behind. The friction on ground will be on the forward direction. Obviously this F are same, this F and this F are same, right? So here also we have to understand why these are forward and backwards. Okay, so now you try to understand roller is rotating. Okay, and this is the contact that has happened, and the workpiece is entered with some velocity v1, and it is rotating with some omega, and that, let us assume that we are velocity of roll is equal to r radius of roll into omega of the roll. When you're trying to enter, who will have more velocity? VR will have more velocity or V1 will have more velocity when you're touching it? Who will have more velocity initially? Guys, who will have more velocity? Whether roller will have more velocity or the workpiece will have more velocity initially when you're entering. Obviously roller will have more because roller is already rotating. Yes. Now if roller is having more velocity, right, if roller is having more velocity, in the sense I can assume that the this is like this, like I can assume this is ground and roller is rotating like this, right, right. But we want friction on the workpiece, we don't want friction on the roller, because we don't want to, I don't want to care about roller, I want to know what is friction that is acting on the workpiece. So now I can say that, now I can say that roller is some kind of a ground, roller is some kind of a ground, and this ground is moving faster here, in the sense the relative velocity between the workpiece, this is workpiece, this is workpiece, is it means that if you're sitting on roller, you feel that the workpiece is moving backward, isn't it? If you see that, if you're sitting on roller, you're sitting on roller, and if you're seeing workpiece, as roller is rotating fast, you see that workpiece is moving backwards, isn't it? Right or wrong? Yes or no? Guys, are you getting my point? Roller is rotating very fast, you're sitting on roller and you're seeing the workpiece, even the workpiece is moving forward, but as roller is moving more faster, you see that workpiece is going back. Yes or no? Yes. If the workpiece is going backwards, the friction will be in forward direction. Am I right? Etc. Yes or no? Workpiece is going backside, in the sense the friction on the workpiece will be on forward direction. Is that right? Yes. That's the reason. That's the reason why. That's the reason why the friction on the workpiece in the leading zone. This is called leading zone. Why it is leading zone, I'll tell you. But initially, when the workpiece is entering into the roller, two rollers, the friction on the workpiece will act in the forward direction. It will be in the forward direction like this. Okay. As you keep on moving, as you keep on moving, what is happening? As the volume is the here, if you see the volume is like this, right? And as you keep on going like this, the height is reducing and length is increasing, right? Height is reducing and length is increasing, in the sense initially the length is L1, finally is L2. L2 divided by time, L1 divided by time. Initially the length which is going inside is less, then L2 is more because of that volume compression. L is increasing, in the sense velocity of workpiece will increase than the roller. Okay. So what I'm saying is that initially you told that roller is having more velocity. It means roller is having more velocity than V1 initially. What I'm saying that at the exit point, what I'm saying is that V2 velocity of workpiece is more than velocity of roller. In the sense, roller will be having less velocity than the exit velocity. Are you getting this point? Yes or no? Please tell me. Okay. Now you sit on roller. Now who is moving faster? Now who is moving faster? Obviously this is moving faster. As this is moving faster, you see that friction is in backward direction. Am I right on the workpiece? Yes or no? Yes. So that is the reason why there is an forward friction and there is backward friction. Obviously forward is becoming backward, in the sense that there is some point where the friction has to be zero, right? Right. And that is what is your sticking point. That is what is your sticking point, in the sense the velocity of roller, the velocity of roller is equal to velocity of workpiece. From that is why this two zones have converted. Leading zone, the leading zone. Okay, the leading zone is this. So this is what is leading zone. This is what is leading zone. And lagging zone, lagging zone. So this is what is lagging zone. In the sense, workpiece is faster than the roller. Okay. So if I say if I see in this zone, velocity of workpiece, is less than velocity of roller. In this zone, velocity of workpiece is greater than velocity of roller. So the place at which that is happening, some place, velocity of roller workpiece will be equal to velocity of workpiece. And that plane, why it is called plane? Because it is, we have drawn in 2-dimensional, but it is a 3-dimensional thing, right? So the, because we have roller like this, we have rollers like this. This is what is your workpiece, right? This is what your, this is our workpiece like this. We have rollers like this, right? So this is a plane. This is a plane. The plane at which the velocity of roll is equal to the velocity of workpiece is known as neutral plane. Neutral plane. Okay. And the plane in which the friction on workpiece also is changing its direction. Initially, the friction will be in the forward direction, and next it will be reversing its direction. I told you clearly why it is reversing, because the velocity of workpiece is increasing. All these things I told you clearly. Okay. Now the important point that you have to understand here is, this is the center of roller, and this is the starting point at which the contact is happening. This is the ending point. The ending point is the contact is ending. So roller the roller is subtending some angle. This is the starting point, this is the ending point, right? The roller will be subtending some angle, and this angle where the contact is happening, so this is where the contact is happening. Contact between workpiece and tool, contact between workpiece and roller, not tool, roller, right? So that angle theta, that is that angle subtended for the contact here, is known as bite angle. It is known as bite angle. Okay. And also if you see the point at which the neutral plane, this is called neutral plane, no? And the point from neutral plane to this point is known as angle of nip, but as of now we don't remember that. That is also having some angle, but we have to know this is what is bite angle. Bite angle, bite in the sense like the roller is biting the workpiece, or workpiece is biting the roller. There the contact is happening. Okay. So that is what is contact. Okay. So there is a slip. Obviously, why there is a slip? Because roller is going faster, workpiece is going slower. Obviously there is a slip, and that slip is calculated by velocity of roller minus velocity of velocity of workpiece, that is inlet velocity, by velocity of roller. And forward slip is nothing but, here the slip is moving forward because workpiece is going forward, right? So the velocity of workpiece minus velocity of roller by velocity of workpiece into 100, that is what is backward slip. Okay, fine. So this is how this complete diagram has been explained to you. Okay, please do remember all these points what I've told. If you are having any doubt, please revisit this video and try to understand wherever you are getting some doubt. Okay, I have explained clearly. As for me, I have explained clearly. Okay, so now let's do some calculations. Let's not go into derivations. I'll tell you some important formulae. That's it. The first important formula that you have to remember is this one. That is L is equal to under root R delta H. So let me tell you what are this. This is nothing but length of contact. Length of contact. And this is the radius of roll. Radius of roll. Okay. Delta H is change in thickness, that is H2 minus or H1 minus H2. H1 minus H2, the change in thickness. This is H1 here, this is H2. The change in thickness is delta H, right? So what is length of contact? Length of contact is this. This is length of contact actually. But in reality, the length of contact will be like this. But for our calculations, we are assuming it to be a straight line like this, because the angle will be very small like this. So we are just assuming it like this. instead of considering this curvy one, instead of considering this as L, we are considering this as L. Okay, that you have to understand. Okay, so important formula, that is L is equal to under root R delta H. Another thing is you want to find this bite angle. They might also ask you to find the bite angle. So for bite angle, this is the formula: cos theta is equal to 1 minus delta H by 2R. 1 minus delta H by 2R. You have to write these formulas. The derivation is there. Let's not go into deeper. We have limited time. I'm sorry for that. We can discuss that if we are doing some gate and all. We can discuss that. But for this, I'm sorry, I couldn't go in details because we have to have lots and lots of time to discuss this in detail. As of now, for the sake of examination, you have to remember these two formulas. Okay. Next. And also one more thing you have to remember is that reduction. This is called reduction. That is delta H1 minus H2 by 2. That is what is reduction that is happening in this direction. Here also delta H by 2 will happen. So total reduction is delta H. Delta H by 2 plus delta H by 2 will give you delta H. Okay. So please do remember. Okay. Now. So yeah. Fine. Now. So if you see the sugarcane guy, the example of sugarcane guy, there are two rollers like this. He simply places that sugarcane, bar like this, and he'll go from this side and he'll stand here. Automatically, this will come in this side. So that is called self entry. Have you ever seen that? He doesn't push from this side. He doesn't push. He'll just put it under two rolls, and then it automatically come here. He'll go and wait on the other side. Have you seen this anytime? Yes or no? Yes. So that is called self entry. So if for us in our case also, if at all the workpiece wants to enter by itself without any push from the backside, that is called self entry condition, and that self entry conditions will be achieved when this condition is satisfied. That is, your change in thickness is equal to coefficient of friction between workpiece and the roll square into radius of the roll. If this condition is equal, or sometimes you can say if it is greater, but the limiting condition is this: if your condition is exceeding, I mean, if your condition is satisfied like this, delta H is equal to mu square R, then it will go into self entry zone. It will go into self entry zone. Is it clear, guys? In the sense, what I'm saying is that obviously it should be like this, but limiting case is this. Yes. So please do understand this. This derivation is written here, but because here we have to resolve the equations and all, then we have to do mu p cos theta, all these things we have to do. But anyways, I'm not doing that. So the condition is this. Okay, self-entry case. Next. So this is what I've shown in the previous class itself. The grain refinement is happening, and this is called recrystallization. And the recrystallization temperature TR is equal to, almost equal to, what is that? Anyone? Is almost equal to what? Anyone? Can you recall the previous class? I've discussed something. Guys? Is it not Tm by 2, melting point by 2? Yes or no? Is it not melting point by 2? Yes. Yes, we have discussed in the previous class. Fine. So this is what I've clearly mentioned about neutral plane, all these things I mentioned. Okay, you just go and read. Just whenever if you have whenever you're rewatching this video, or maybe if you're going to this point, take a snapshot or pause the video and write all these notes and try to understand all the points that I've explained have been written here. And the important point that you have to take care here is this, because we are thinking in reality we are thinking that this is the roller. Okay, these two are the rollers like this. We are putting some thickness like this, and we are thinking that the thickness will come like this. and we are thinking that this distance is equal to this distance. But no, what will happen, because of elastic recovery, what will happen is that it won't come like this, it will come little larger, little bigger, because of this is what is your elastic recovery. The material cell. So the thickness will be little higher, but we are not considering this thing in our calculations. But in reality, this will happen. In reality, that will happen. Okay, fine. Okay, these are some problems. We can discuss these problems as we keep on moving it. So these are some problems, some problem, some problem, some problem. Okay, now let's discuss about uh, different type of rollings. So this is called two high rolling mill. We have already seen this till now. In the previous few slides we have seen this, that there are two rollers and some workpiece which is having some thickness is coming in between, and then the thickness is being reduced and length is being increased, and we are keeping on doing. This is velocity of roll, this is inlet velocity, this is outlet velocity. We have seen this. And if you want to further reduce thickness, because obviously if your rollers are like this, you can't keep sheet of this much thickness, right? You can't do it. So we have to pre-roll it, right? So there's a limit. So obviously there is a rolling limit. You can't go beyond certain thickness. Let's say if you are having some 10 mm thickness and you want to go to 0.5 mm thickness, you can't go from 10 to 5 mm thickness in one go. You have to do some other intermediate rollings. Then only you can achieve this kind of large reduction. How much is the reduction? 9.5 mm is the reduction. Sorry, this is mm. Okay. If you want this kind of reduction, you have to do in intermediate stages. We can't in a single go, you can't do that, right? So for that kind of situations, we have this kind of three lower system. That is, you first you reduce 10 to some 5, then 5 to some 1, like that you do, and that is what is called three high roll milling. The same thing is being done. So what is this question? What material is used under rolling? Okay, iron heating and letting them in, like that. I didn't get you. And I mean, what is the material used in rolling? That is okay. So you can use any material. You can use mild steel, aluminium, whatever material you want to use. It doesn't matter. You can do that. For what is that? Another question you asked, I didn't get. Iron, I didn't get. What is that? Yeah, we heat. Okay, fine. What you are saying is that whether it is a hot rolling, cold rolling, that is what your question is. Is it that? If you're heating it, it is hot rolling. Yes, if you're heating before rolling, it is called hot rolling. I told you in the previous class only. Hot rolling, if your temperature of working temperature is greater than 0.6, if it is more than this 0.6 of melting point, then it is hot rolling. Didn't I say this? So if you're heating the material before rolling, then it is called hot rolling. Okay. Yes. And because of that, there are some defects, because hot rolling, your rollers will be heated. Obviously you have to apply some kind of lubricants and you have to apply some kind of coolants, that will be there. But if you want to deform your material easily, obviously you can preheat them, and then you can send through the rollers, it will easily deform. That is called hot rolling, hot working. It's called hard working. If you're not heating it, then cold. If you're little bit of heating you're doing, then it's called warm. Okay, we have seen these classifications in the first slide of our rolling metal forming, intro to metal forming. Okay, if not, you go to previous lecture and see the ending, the last 1 hour of our this thing, you get that. Okay, now this is for high roll mill, because you want large reduction. Why in the first case, why we are doing these two things? Because sudden large reduction is not possible, because rollers have some bearings here, Rollers are mounted on some bearings. If you're sending some large one, this bearings have some forces, right? They have some forces. They'll have to be intact. Otherwise, there'll be some kind of failure on bearings. If bearings are failure, then the rollers will come out. You can't do that, right? So to sustain that kind of a thickness, what you say, reduction, right? You have to have that very high reduction. Then what do? You have two rollers that are doing rollers, then support them with some support rollers. Obviously, two bearings will be there. So obviously, this support roll will help you. The other rolls to do this, rolling happily or reduce the thickness. So these are called 4 high milling rolls. And this is another extra two supporter. Instead of one support, two supports have come. Cluster mill, tandem mill, keeping on going. I want I'm doing from 10 to 5, 5 to 3, 3 to 2, 2 to 0.5, like that. I can keep on going it. Finally, I'll achieve it. And this is continuously going, continuously tandem. Okay, good. Next. So what are the other things that we can do with rolling? Not only machining or lathe machine can perform the threading operation, even rolling also can be used to make the threads. See, that is what we have seen here. If you see here, this is a fixed die, and you have some threaded, parts. This threaded, thing that has been printed on this die, and other part also will be there like that only. And if you're trying to put some kind of a bolt, starting blank like this, and then roll, just move this thing. Okay. Yes, you're right. Yes, you're right, Naveen. Pottery. Pottery is not because of rolling. Is it because of rolling, Naveen? No, it isn't. I think pottery. How come it will come under rolling? I don't know. Rolling is like you have to have two rollers. Pottery is by some rotating uh, thing will be there, and then you shape it out because it's an axisymmetrical rotation that is happening. Then with the help of hand, you're shaping it out. But I don't know. I can't. I don't. I'm not sure whether we can classify the pottery under rolling, because is it because this rolling is having some deformation. Pottery, I think you don't have any deformation there. You're shaping it out, right? You're not deforming it. Are you deforming it? You're deforming it, but I'm no. I'm good question. But I don't know. I'm not sure whether we can classify pottery into rolling operation or not. Okay, let me check. Let me check. You also check and let me know if you can find the answer. Thank you. So that is how you can find out we can do the threading operation in the rolling also. Okay. So the problem with rollers is that if your thickness, this bend of rollers will happen because this thickness is the reduction of thickness is very high. Let's say material, this kind of bending will happen. So once after rolling, what will happen? Your cross section should be like this. Instead of cross section of workpiece is like this. I mean, I'll draw in a 3 dimension. Like instead of having cross section like this, it'll have cross section like this. Okay, let me draw it neatly again. It'll have like this. This is how the cross section will look like. Okay, instead of this. So to avoid that, what I'll do, I will give some camber to rolls. Camber roll is in the sense instead of rollers putting like this, I will give the rollers like this. But once the workpiece is coming in, then it will become flat like this. And this is called camber. Hence, these are called camber rules. Okay, so that is what a problem. This is the problem, and this is the solution. Okay, this is the problem here. Solution by providing camber. Good. Next, what are the defects in rolling? So you can see this kind of wavy plate is not the sheet which is coming out from the rolling is not straight, it might have some waviness. So that is one of the defect, right? And another is cracks. You see there are some kind of cracks that are occurred onto the sheet because of insufficient cutting fluid. The cracks might be forming, and edges, this kind of edges are formed because of anisotropy of material. This kind of edges also are formed, or sometimes they'll split up like this. The part, if you're having this thing like this, they'll split up. That this will go up and this will come down, and that is kind of like opening like a mouth of an crocodile, right? So that's the reason why it's called alligatoring. This is what is called alligatoring or crocodile cracks, because it is opening its mouth like a crocodile or alligator. Okay. And another thing is called spread. What is spread? If you're looking from the top view, I told you already, the B is not changing. The thickness before and thickness after is not changing, but sometimes the spreading will occur like this. Instead of, this is some B1 plus some delta, some B. Obviously, if your spreading is happening here, then B1 will not equal to B2. So that is one of the defect, spreading. Okay, fine. So that's the end of rolling. Any doubts till now? Rolling? Okay, good. Next is nothing but wire drawing. So what is wire drawing? Here and also please remember, rolling is bulk metal forming operation. The previous one what you have discussed is bulk metal only. It's not sheet metal, right? Fine. So in uh, bulk metal forming operations, second one is wire drawing. First one is rolling that we have already discussed. Second one is wire drawing. Okay. So here it's nothing. There we are reducing the thickness of sheet. Here thickness of slab. Yes. Here we are trying to reduce the diameter. That's it. We are trying to reduce the cross-sectional area, not the diameter, cross-sectional area. Initial cross-sectional area is like this, let's say. The final cross-sectional area will be like this. Let's say initial cross-sectional area is this much, the final cross-sectional area is this much. Or initial plate is like this, the final cross-sectional area is like this, because you are providing some kind of slot like this. You are entering like this and it is coming out like this. Okay, you're changing the cross-sectional area. That's it. That is what you're trying to do in the drawing, wire drawing. But drawing, that is what you're doing in drawing. But wire drawing is nothing but simply change in diameter, reduction in diameter of the wire. That's it. And it is called drawing. Why it is called drawing? Drawing in the sense you're pulling something. Drawing means you're trying to pull something. So that's the reason. Initially in rolling, what we did, we are trying to make it entry here. Maybe we are not entering, we are maybe giving some push from the left hand side like this. Or sometimes in a self entry case, we are when delta h is equal to mu square r, this is the condition, right? If this is condition is satisfying, then obviously self entry is going up. But in this case you have to draw in the sense you are applying your force. You're drawing from here, drawing from here, pulling from here, drawing or pulling. So you are applying force in the exit. So this is entry, right? This is entry. Yes, drawing also can be hot or cold. If the material is softer, no need of heating anything. If material is a little harder, then obviously you are going to heat it and then draw it. You're right. Okay. That's why when I've discussed about hot working and cold working, I didn't say hot rolling, cold rolling. I didn't say hot drawing. Working is nothing but forming. In forming, we can have rolling, we can have wire drawing, we can have extrusion, we can have anything. So that's the reason why any metal forming operation can be done using using in the sense like by heating the workpiece, or by not heating the workpiece, or maybe little bit of heating the workpiece. The little bit of heating the workpiece is known as warm work. Okay, is it okay, Aravindan? Yes. Fine. So please remember, again I'm saying we are trying to pull from exit. We are pulling from the exit. Okay, we're not doing anything here. We are not doing anything here. Sometimes we are pulling this side also, that is called the back stress, but mostly we'll avoid it. Sometimes we'll use this back stress. I'll tell you why we are using this back stress anyways. So we are pulling this, so here only we have to calculate this drawing stress. This is what is drawing stress. You have to calculate that how much is the stress that we have to apply from the pulling side, so that this wire will come out, the direction and diameter will come. But before that we have to understand the system. There we have rollers. Rollers are rotating. Here we don't have any rollers. We have a die. We have a three-dimensional die like this, like this. Okay, something like this. Okay, something like this. And of course this, oh sorry, and die is not, it should be circular, man. Sorry, it should be circular like this. Sorry, something circular like this, because this is circle coming out. No, yes, it should be something some circular like this, circular. Okay, so fine. So it is also having some die, and through the die you're pulling it. And how can I say that? Oh, I can, I'll tell you one example, but it is quite opposite to that. Yeah, through a circular hole. Have you ever eaten mixture, man? Like you might have seen that snacks items, some kind of, it will be like this, which is some kind of orangish color. You uh, make the batter, you push it through holes. You push it through holes and you do like this, and then you push it through hole and you put it in very hot oil, then it will fry itself, then you remove it and you eat it. Yes, what you're doing, you assume that the batter is your workpiece. Okay, noodles also, yes, you're right, noodles also will do like that only. But this, that example what I've told is, I don't know what you call in English. Generally it is very famous in South India. I don't know about North India, but it's very famous in South India. Okay, so let us assume that batter, which is made up of some chana dal, all these things, will mix it. If you know some ingredients of that cooking, you add some chana dal, some rice flour, some some kind of chili powder, all these things you'll add, you'll mix it, and then you make that dough, right? You make that dough, and then you put it in between some kind of like this. There's some kind of cylindrical thing, and holes will be there here. Remember, holes will be there here, and you put your batter like this, and there is some kind of a setup pistons like this. This is one piston attached to this, and this is another piston attached to this. When you press it with hand like this will come out. Have you seen that? Yes. So this is analogy, you have to understand. Rolling analogy we have discussed with sugarcane juice, right? So we can relate it here also, we can relate it, but here we are pushing it. Okay, we are pushing it through something, and it is coming here. So this is whatever that thing is called extrusion actually. Okay, but here what we are doing, we are pulling. We are not applying any force here for drawing. We are trying to pull from this side, so that is why this is called drawing. But generally if you're applying force from here, then it is called extrusion. You are trying to push from the exit, from the entry. If you're trying to push from entry, then this is called extrusion. If you're trying to pull from exit, then this is called drawing. Is it clear? The differences between drawing and extrusion is not, there's no big deal. The only thing, the wherever you're trying to apply your pressure, or wherever you are applying your stress, that is what is important. Okay, is it okay, guys? Yes, very clear, I know. Fine. Now there are some zones here. So here again, before, this is called lubricating zone. Why it is called lubricating zone? Because you are trying to apply some lubrications here. You want to apply some lubrications here, so that it is trying to go enter, and happily it is coming out from this thing. and this is deformation zone. This is sizing or deformation zone. Okay, so the zones will be discussing in the next slide. So please do understand the diameter d naught is reduced to diameter df. Obviously df should be less than d naught. That is what is happened. Okay, fine. So the zone 1 is deformation zone, lubricating zone, and sizing zone. So okay, this is deformation zone, lubricating zone, sizing zone. This is where the size has occurred, sizing zone. Okay, so let's you discuss all these things. There's nothing but in deformation you're applying. The deformation is happening because there's change in dimension, like there's a gradual change, and this is called your diangle here. This is called your diangle, semi diangle actually, if you say semi diangle. Okay, semi diangle. Fine. Okay, in this not only rods, not only wires, we can pull tubes also. Tubes are what? Hollow cylinders, right? We can even pull the tubes also. But what is the problem with tube? If you're simply drawing a rod, it is full solid rod. We are caring about only outer dimensions. We are caring about only our dimensions. But if you're pulling a tube, outer and inner both have to be taken care of. Yes, yes or no? Internal holes also have to be. So the outer dimension d naught and the inner dimension di both have to be taken care of. And it sir, I won't care about, sir, I'll just pull, sir. If you're pulling, the thickness has to be proper, right? The thickness has to be proper. Outer dimensions are maintaining. So you wanted to have some 10 mm diameter outside. Okay, sir, it is maintaining. How good you're maintaining the internal, how good you're maintaining this thickness. The thickness along this circle has to be maintained properly, right? Right. So there are three ways we can do that. One is called mandrel. You just put some kind of an object here like this in between, and this mandrel is fixed. It is here, and now you put some kind of a tube, just tube of some bigger thickness, and then it will come to this kind of thickness, or maybe it will come to this kind of thickness like this. Okay, so the tube is having outer dimensions are maintained by this die, internal dimensions are maintained by this mandrel. So good proper dimensions will come out. Okay, and you can pull like this also. You can directly pull through a die without any mandrel. But what is happening? If you are pulling without mandrel, the internal dimensions will not be coming up properly, isn't it right? Because we don't know what is happening. Yes, and sometimes you can also use this mandrel as floating for some reasons, some friction reasons, because here the mandrel is fixed, but here if mandrel is floating and here and there, when only it will come into action when only you're trying to pull with some forces, right? So you can also use floating mandrel as well. Clear? Good. Fine. Now let's go to extrusion. This is what we have done in the previous. We made one nice snack item, right? In the previous slide, we have made some dough with all this mixture and all. We mixed with nice dough, and then you're pressing it and you're putting it in oil. Same thing. It's a toothpaste also. What you're doing with toothpaste? What you're doing with toothpaste? You're having some tube like this, right? You're having some tube like this. What you're trying to do? You're having tube like this. What you're trying to do? You're trying to apply force here, right? Paste is coming out. Am I right? Same thing. Same thing. Extrusion is nothing but you're putting your workpiece here, and this is what is your container, toothpaste container, right? And this is where the internal, the entry point. You have opened your lid. Katam, from behind your with syringe, you're pushing. Syringe also is kind of an extrusion. Syringe, right? Your syringe is having something like this, and some needle is here, right? And then you have some kind of a piston, and you're pushing it. Happily, that liquid is going into your body, whatever it is. Everything we can take so many examples for extrusion. Okay, so Here again I'm telling this can be cold, warm, or hot based on the material that you are selecting. Fine. Now, extrusion again is a bulk forming operation. See the example I clearly told, squeezing toothpaste from toothpaste tube, right? 1 minute, guys. I have some call. Okay, guys, are you here? Very good. Let's continue. So in extrusion, we have two different type of extrusions. Okay. So what are the two different type of extrusions? That is nothing but not two. Yeah, two only. In that we have other extrusion, and then we can yeah, we'll discuss that little later. Now we'll discuss about this. Okay, fine. One is direct or forward extrusion, another is indirect or backward extrusion. By direct diagram itself, we'll be able to understand. Forward is that what we have been discussing till now. What is that? We are discussing this. There is a ram, piston kind of thing. We are trying to apply the force onto the workpiece, and it is contained in a container. And through the opening or a slit, it is opening, and the workpiece is being flowed, or it is being trying to go like this, right? Now, this is forward. The problem with forward is, you see, this is the place, this is the circumference, this is, let's say this is a diameter, so this is the circumference, this is the circumference, this is the circumference, right? The top circumference. We can see, if you see from top view, it is like this circumference, right? So that circumference is having some kind of friction throughout, am I right? So the friction between container and workpiece is there, right? This is where the friction will be there, friction mu. And as you're keeping on moving, the workpiece is keeping on moving, and as your workpiece is, you're pushing this side, the friction will be in this direction. So whatever the force that you're trying to apply should be applied in such a way that this frictional force also should be overcome. You have to overcome the frictional force. It means that you have to apply a little extra force. It's not only the force that you have to apply to make sure that this is coming out. You have to apply some force. Obviously, let us assume that the force that is coming out here is F1 and it is SA. This is the input force that you have to give, F is equal to F1 plus F. This frictional force has to add it, because you have to overcome the friction also, right? So that is the why, that is the reason why I don't want this to slide. Why it is coming? It is coming because this object is trying to slide with this container, because the rubbing action is happening. So this workpiece is sliding with respect to container. I don't want to happen that. I don't want to happen that. So what can I do? What can I do? I can do this. Another setup. It's a very nice setup. I'll tell you that. This is what you can do. Here the important point is, you're applying force in this direction. Your extrusion also coming in this direction. Both are in same directions. Applying force in right side direction, extrusion also in the right direction, right side, same directions. But if you see here I will apply load like this now, and extrusion will come like this. And you see, there is no relative motion between the workpiece and the container, isn't it? Can you see that? There is no relative. As there is no relative motion, there is no friction. As there is no friction, no need to apply extra force which can overcome that friction, right? So you have avoided that. So that's the reason why we are doing this backward extrusion. Just it's like what you do, how can I say this? Any example that we can say? It's nothing like, you take some dough, put it dough here, put some plate, have some hole, push the plate now. If you're pushing the plate, the dough will come out like this. Am I right? Am I right? Yes. So that is what is this indirect extrusion. You are avoiding this relative motion between the workpiece and container, so as to avoid or reduce the force compared to the direct extrusion. That's it. Very easy. Next Next is hydrostatic extrusion. So what is hydrostatic? Hydrostatic is nothing but, sir, force is here there's relative motion. No, what I'll do is that I will make the fluid fill like this full, and then apply liquid force to this, and that force will apply into the liquid will pressurize this workpiece, and it will go inside. And why you're doing this hydrostatic? Because hydrostatic pressure will reduce the friction. Obviously there is no friction, that is where that important thing. And if you're applying pressure, hydrostatic pressure, the material's ductility will increase. Don't ask me why. It's a very big detailed explanation, not now. Please remember this is a thumb rule. That is, if you're trying to apply at hydrostatic pressure on some workpiece, the ductility of that material will increase. So if at all this is a brittle material, let's say, instead of heating it, you just apply a hydrostatic pressure. Because of even pressure that is applied onto the workpiece, the ductility of the workpiece will increase. There's a big explanation for that. You can read this thing in plasticity. There is a course. If you're doing your masters or somewhere in higher studies, if you go and read the fundamentals of plasticity, you'll know that, but not now. Okay, let's have it as thumb rule. So the only problem here is leakage. It should be airtight. No fluid should not come out, right? So this is one more way we can extrude hydrostatic extrusion. We are filling with some fluid, and then we are trying to apply the force through the piston or the ram. It's called ram, not piston. Okay, ram. And then the fluid is getting some pressurized fluid, and the pressurized fluid is applying pressure on the workpiece, and then it is moving, and we are trying to avoid the friction also here, and the ductility is also increased. Okay, next, impact extrusion. What is impact extrusion here? Impact extrusion is nothing but, here we are gradually applying. In the sense, if this is time and this is force, we are gradually applying, and then we got saturated, and we'll keep on applying. We don't suddenly apply. But impact is nothing but we suddenly apply the force. How, sir? How we are trying to apply suddenly? Nothing but you have okay, this is the punch, this is the die. Tell me, is it a okay, it's already written now backward. Okay, so you take this punch to certain height and leave it. Tuck, it'll hit. Right? Is it right? Like that again, go up, down, up, down. You go up and leave it. Under gravity, mg, that is your force, right? You don't need to apply any force. Mg, tuck, hit. Like that you do repeatedly for some time. Then obviously backward extrusion, no, this will come. Forward also you go up, punch, up, punch, up, punch, up, punch, like that. Okay. So this impact extrusion, no, generally in previous times, if you see, your toothpaste tubes are made up of metals. Have you ever seen? Even now also some toothpaste tubes are made up of metal. Is there any toothpaste that is making the toothpaste tubes as metal? Now Colgate, this Pepsodent, all these things are uh, generally plastics now. But in the olden days, or maybe in some of the toothpaste are still using toothpaste tubes as metals, right? So these toothpaste tubes are manufactured by using this impact extrusion actually. So how it comes out these metals? I didn't get you. So you are saying this metal you are putting here, some lump you have put here, then you are trying to apply. So this is what is your tube now, isn't it? Is that your doubt, Naveen? I didn't get your doubt. Or your doubt? Yeah, this is what is metal. You're trying to apply force, and there is a space. Obviously, there is some space between here. Then through the space, this is coming up, and tube is formed. This is diameter, okay? Diameter like this. Tube is formed. Okay. Even some ointment also. If you see, there those very the tubes are made up of the metal, right? Those are manufactured by this impact extrusion. Okay. And analysis, I think they won't ask in exam, but anyways we have to know that basics. This is what is drawing stress for analysis of wire drawing. What is drawing is nothing but, I told you clearly, you are pulling from the exit. Okay, you're pulling from the exit. This is what is your die for the drawing, something like that. Okay, you're pulling from the exit. Drawing stress is given by mean flow stress into A plus B ln R. What is A and B? Some Johnson's constants. R is nothing but extrusion ratio or drawing ratio, whatever it is. Extrusion ratio. Extrusion ratio is nothing but initial area divided by final area. Initial area, what area? Cross sectional area. Initially this much is cross sectional area. Okay, finally cross sectional area is AF. Okay, initial cross sectional area by final cross sectional area. So to do the analysis, we'll use slab method. We take all this, strip here, that analysis, summation of forces in x direction is equal to 0. We are applying all these things, and then finally we are finding the solution as this. And still yet don't need to remember this equation at all for your HL examination. But the only points you have to remember are boundary conditions. So these are the boundary conditions that you have to remember for the examination sheet. What are the boundary conditions? This is entry, and this is where the deformation is happening. This is exit. This is what is your this what you say, the slab. Okay, this is what is this, something like this. It is something like this. Okay, fine. Okay, so you're pulling from here, sigma d. So what are the, this is inlet I, this is outlet O, right? So everything is x direction. This is an x direction, right? So at, this is Ri, you know that, and this is Rf, final radius Rf, right? Sorry, half, not full. Full is diameter, right? So this is Ri and this is Rf. Okay, so initially when you're applying here, sigma x is equal to 0 generally, but I'll apply some back pull like this, back pull, that is sigma is equal to sigma d at R is equal to Ri. If you're applying back pull, if you're not applying back pull, sigma x is equal to 0. If you're not applying back pull, sigma x is equal to 0. If you're not applying it, if you're applying it, it is 0. And at exit, sigma x is equal to sigma t. This is what you have to find out. So that those are the boundary conditions. Those are the boundary conditions. Okay. Fine. So for extrusion, boundary conditions are, you're applying, you're trying to find sigma x is equal to sigma e. This is what you have to find. Entry. Exit, I'm not doing anything. So sigma x is equal to 0. Is it clear, guys? The boundary conditions are clear or not? Why I'm telling you about boundary conditions means, the boundary conditions indeed are explaining that extrusion, you're pushing it from the entry point. Drawing, you're pulling it out from the exit side. That is how you have to remember. That is what he's putting into equations. That is, those are called boundary conditions. That's it. Okay, fine. Let's proceed. So this is what is the diagram for direct extrusion and the indirect extrusion. The indirect extrusion is nothing but that opposite, right? Like where there is no relative motion between the container and the workpiece. We have seen that, right? So obviously, as ram pressure, this is ram pressure, okay, and this is your ram stroke. Ram stroke is nothing but the movement, the piston movement. The piston movement is in this L, x direction. Okay, ram stroke. As you're moving forward, pressure is keeping on increasing. So for direct extrusion only, you see more. Why it is more? Why it is more for direct extrusion? Anyone? Why the pressure is more for direct extrusion? Anyone who can tell me? Who can help me with that? I told you already clearly in the previous slides. Can you help me? Yes, friction is there in the direct extrusion. So this is the extra force, extra pressure that is you have to apply to overcome friction. Okay, very good, very good. That's the reason why indirect. This can also be a question. This can also be a question. They'll say, what is this? This belongs to what? Hydrostatic, indirect, direct, whatever they can ask. Anything they can ask. Okay, fine. And these questions we are not doing. And the defects of wire drawing are nothing but surface cracks, because when you are doing the drawing, surface will be having some cracks, and sometimes there may be the seams may be opening up during the operation. In the sense, when you're doing these things, there might be some kind of breakage, and then maybe coming out. Okay, those are called seams. Are what do you mean by seams? Okay, seams are nothing but I should show you the diagram. I don't have diagram. Huh? Okay, I'll show you the diagram tomorrow. Okay, and residual stresses also will be there. When residual stresses will be there? When you're doing the cold drawing, because you're not heating it. As you're not heating it, you have to apply more and more force, because it is little harder. If the workpiece is little okayish harder, let's say, and you're not heating it, you're trying to extrude, or you're trying to do the wire drawing. Now, if you're doing that, you're trying to apply more and more force. As you're applying more and more force, the excess force is increasing, and it is reaching the ultimate strength is more. It is trying to get more and more ultimate strength. Because of that, the stresses that are accumulating inside will be increasing, and because of the residual stresses, there might be a chance internal residual stresses which are compressive in nature, they want to relieve themselves. If at all there is a defect that is formed inside because of casting, because obviously this billet what you're trying to put is made up of casting only. If there are small gas bubbles or maybe some crack inside the casting, and when you're trying to apply some force because of internal residual stresses or the compressive stresses, what will happen? This points will be acting as the point of initiation of crack, and then it will propagate. That's it. It will get failed. Okay, so that's the reason why wire drawings have this kind of effects. That is the reason why we have to preheat before doing the wire drawing in most of the cases, but in some cases it's not allowed. So then we have to do some other things where we can avoid this residual stresses and all. Yes. Next is extrusion defects. Extrusion defects are nothing but, you can see here, center burst. See, there are some holes that are formed in center, and this is called piping. Okay, surface cracks. All these things are the defects for extrusion. Okay, and next is forging. Okay, actually, what is the time? Okay, we have. So can I? It's already 10:38. Can I extend for some 15 more minutes so that we can make up the initial part? Today we have started a little late, right? Can I extend a little more, guys? Okay, please. Thank you for that, because today my laptop was having some problem, right? So I'll extend little more so that we can cover up some more syllabus. I won't extend more. Let me take some 10 to 15 more minutes. That's it, and we'll close it off. Okay. Okay. Now let's discuss the another bulk metal operation. So how many till now? How many have we discussed? We have discussed rolling. We have discussed rolling. We have discussed wire drawing. We have discussed extrusion, right? And the another thing that we're going to discuss today of bulk metal operations is forging. Bulk metal operations is forging. Okay, so here you see forging is been with us from decades, not decades, centuries. Okay, so what is that? Simply take a workpiece, put it under some dies, put it under some dies, and then when you are trying to apply force, and let's say if you're putting the one die on fixed ground, and then you're putting a billet, and then you're putting the upper die and then applying force on top, what will happen? Obviously, the let's assume that this is a circular thing like this, and let's say it's having some radius r and some height h. What will happen here? Height will reduce, h2, h1, r1, radius will increase, isn't it? Height will reduce and radius will increase. That's it. This is called open die forging. Why this is called open die forging? Because you don't have any restrictions on any other sides except the side on which you're trying to apply the force, right? And closed die forging is nothing but you have some kind of a shape. So this is kind of a dumbbell shape, right? You want to make some dumbbell shape, and you have put some the top die will be like this, the bottom die will be something like this, right? And you have some, you put some material like this, and then you apply force, then it will take into this shape, right? So this is called closed die or impression die because you are making it close in closed environment. Flash, and this thing that is coming up here, you see this thing is called flash, and that is useful in some cases. It will try to absorb some other unwanted forces that is generated, and sometimes you don't want that flash to be generated, and that's why it's called flashless forging. Exact amount of material you'll be putting inside, then pushing it, it'll take the shape of the die. That's it. Okay, fine. So if you see, this is what is happening. Clearly by diagram itself you will be able to understand. Initially you have some diameter d, height h, you're applying some force with velocity f gradually, and then intermediate stage, little bit of increase in diameter, reduction in height. Finally diameter is reduced, height has, so diameter has increased, height has reduced. Obviously we can say df is greater than d naught, and h naught is less than, sorry, yeah, h naught is greater than, wait, d naught is less than df, h naught is greater than hf, right? So that is what is called open die forging. And in open die forging, okay, what is happening? Sometimes, obviously, if you're trying to apply this is circular. If you're trying to have some plate on this line, you're applying some load like this. Obviously, this will try to expand like this. When it's trying to apply, there's a friction that is occurring at this place. Am I right? If you're taking some kind of this thing from here to here, the friction will be this side. Sorry, the friction will be left hand side. From here, the friction will be like this. Here, the friction will be like this. Because of this friction, the material will not move here. It will tend to stick onto the top, and this bulging effect will come. This is called barreling, bulging effect. This is called barreling effect. This is when there is a friction between workpiece and die. Okay, so this is called barreling effect. This is barreling effect. This is also is barreling effect. When will you not have barreling effect? You will have no barreling effect when the friction is almost zero. It's called slipping, and this is sticking. Obviously, there is some friction which is greater than zero. Is it clear, guys? Did you understand the difference between slipping and sticking? So this case was slipping condition, and this is sticking condition. Okay. So this is called closed die. Till now we have discussed about open die, right? This is closed die. I already told you, dumbbell shape, right? So you have some work part, and you're putting it in between some this thing, and then you're trying to, and you have already some pre-shape that is designed onto the die. This is kind of a shape that we have designed onto the die here. On so that workpiece has to take that shape. So it is slowly taking, and slowly flash is generated here. Okay. So this is called your closed die forging. Closed die forging. And this is upset forging. What is upset? Upset forging is nothing but, you see here, you want to make the bolt, you want to make this kind of a bolt here. So initially we have a rod like this, and then you stop here, and this lengthy rod, you press it. When you're pressing it, it is coming to like this. Is it right or wrong? Okay, let me draw like this. This is a full rod, and let me take some this thing, and you stopped something here, and it means that the deformation will not occur from below here. So you're clamping it here like this, and then you're applying force like this, and this has become like this. So now this is rod, this is a bolt, right? Am I right? Yes or no? This is called upset forging. That's it. Upsetting. This upsetting in the sense this is upsetting only. This is upsetting. This is all upset forging only. But here we are putting some block. We are putting some block here. We are stopping here, and then we are trying to push, and we are getting this bolt here. That is what we got here. If you see, series of diagrams will explain that what we have done. Okay. So what you are using? We are using forming heads on nails, bolts, similar products. We are forming the heads. That's it. Next is wedging. Wow, this is a very good one. Now let's say uh, uh, you have some pipes. You have some pipes, and you want to reduce uh, some dimension of pipe here. You want to reduce some dimension of pipe here, let's say, or you want to taper the pipe like this. You want to taper the pipe like this. Now, either you can do that what you say extrusion or tube drawing, not extrusion, tube drawing, or else you can you have some kind of this thing uh, dice. This dice will move in up and down direction. It means some kind of clamp. Both will clamp and both will go up. So it is hitting the workpiece. So gun is like this: hit, remove, and it is moving like this. As you're hitting it will change its diameter, right? So this is what is happening. The diagram will explain. So this dice will move up and down, and you see this. If you are seeing this thing from this side, this is the view. Okay. So in the sense, you're rotating this workpiece like this, and you're making this up and down, this clamping, clamp, unclamp, clamp, unclamp, clamp, unclamp, like that. If you're doing that series of operations while rotating this workpiece, the diameter will be reduced. Okay. And this wedging machine, I have seen personally, are used for manufacturing gun barrels. I visited some Ministry of Defense company where I have seen this wedging machine is used for manufacturing or reducing the diameters of gun barrels. Is it okay, guys? Yes. Next is roll forging. It's a mix of rolling and forging, but it is a forging operation. How? You see here, the diagram itself is again self-explanatory. You want this kind of shape that is formed onto your object. You have a simple rod like this, but after manufacturing, your rod has to, it has to be like this, let's say. So you made that kind of indentations onto the die. These are die, but this die is a roll now. Okay. And as this is kind of a cam, as it is rotating, what is happening? As it is rotating, the impression what is there onto the die, onto the roll, will be formed onto this workpiece, isn't it or not? Yes or no? Yes. That's why it's called roll forging. You're doing forging only, but your die is in the form of roll. Your die is in the form of roll. That's why it's called roll forging. And these are again, sorry, and these are again the application slab analysis for forging, where you take force like this, all these things you'll do, stress and all, we'll do these things, but anyways, don't worry about this, all these things. Yeah. Okay. So I told you there is this slipping and sticking. Fine. So instead of slipping, I'll write without sticking. That's it. Okay. So what happens, as the force increases, only the friction force will come into picture. If your force is not increasing, the friction force will not come into picture, right? So in this forging, what will happen? If you see, there is some place till here. Till here, the sticking is happening. Here, no sticking, means slipping. Okay. Here it is free to expand because there is nothing to obstruct here. Because understood, no? It is free to expand in this direction as it is coming towards the end. As you're going inside, layer by layer, this layer will obstruct this thing. The obstruction will give rise to the stress. As we are moving away from the center, there is no obstruction from here. There is no stress at all, right? So that's the reason why the sticking will occur at from center to certain distance, and that is known as sticking distance. So for sticking, for without sticking, this is the formula. For sticking, this is the formula, and what the sticking length, this is the formula. So let's not worry much about it, but this is how you have to do the analysis. So sir, how do I know, sir, whether it's sticking or not? You find this equation, you substitute this substitute the values in this. This is final height of your this is final height of your billet. This is final length of your billet, and you substitute. If your excess is positive, then sticking is there. Excess is negative, then sticking is not there. That's it. There's no sticking, then it's called full slipping. That's it. Okay. So this is the force for because we are finding the pressure, stress. Then width will be there obviously if you are if at all taking like this slab. So this is height h, right, and you have length L, and this will be width. The other direction will be width, right? So the pressure you are applying onto this into width into dx is this dx. Okay. Anyways, like you are having some kind of slab analysis you have done, right? There the dx will be coming to. What is dx? Dx is this. So this is the dx. This is the dx. Okay, that the thickness here is dx. Okay. So this is the force, and average force is nothing but F by 2 into L, 2 by F by 2 into LW. And if the force is with sticking and slipping, then you have this formula, both the things. From 0 to excess, it is sticking. From excess to L, it is slipping. And the condition what we are using is sigma by root 3, because we are mostly will be using von Mises criteria. Yes. And these are the formulas. And the forging defects are, again, I told you already, it is called barreling. Why barreling is coming? Because of the friction, because of the sticking, this barreling is coming into picture. Okay. And folds in the sense, sometimes if there are some irregularities, there are some folds that are happening inside. Okay. Cracks, because of cold working, cracks are very prominent in the forging, right? So these are the defects. Sometimes you feel that these defects in these cracks are there everywhere, right? In casting, right? In welding also you'll have some cracks. In forging, wire drawing, deep drawing, rolling, extrusion, everywhere you see these cracks. Yes. Okay, so we'll stop here for today because we are entering into sheet metal operations. So in the next class today, we didn't solve any problem because uh, I thought like I started class a little late, so I'll complete some syllabus. So what we'll do is that in tomorrow's class, we'll complete the sheet metal operations as soon as possible, and then we'll solve some questions, theory questions, and some small numerical questions as well in the tomorrow in the sense in the next class. Okay. So that's it for today. If you have any doubts, please let me know. I'm here to answer your questions. If not, thank you. Good night.